Okay, what we're going to talk about is something called the rate expression, rate equation. So if we have a chemical reaction, A plus B reacts to form C, you know that the concentrations of A and B are going to impact the rate of reaction. Well, we want to know by how much, because sometimes the concentration of A might have a bigger impact on the rate of reaction than the concentration of B. And those are called the orders of reaction. Okay, so what we're going to do is I'm going to show you experimentally how we can use data to determine the orders of reaction, and this can only be done using experiments. The way to do that is use something called initial rates. So you can see here we've got the rate of a chemical reaction. You can see the concentration is decreasing of the substance over time. Well, the initial rate is going to be that first part. The initial rate is the fastest part of the chemical reaction where there is the most reactants or the highest concentration of reactants. So let's have a look at an example. So I know here that this chemical reaction is A plus B reacts to form C. So to start with, we've got A, I'm just going to do this, A has a concentration of 1, B has a concentration of 1, and when the concentration of A is 1 and B is 1, the initial rate is 2 moles per decimeter cubed per second. Great. So let's compare what happens when we change the concentration of 2. So if I go from experiment 1 to experiment 2, you can see that the concentration of A does not change. But if I increase the concentration of B by a factor of 2, you can see that that has an impact on the initial rate. The initial rate also increases by a factor of 2. That means because the increase in concentration is directly proportional to the increase in rate, we can say that the order of reaction with respect to RWT, with respect to B, is first order. Or you could just write 1. Great. Just going to change colour. So what about A? So let's compare experiment 1 and 3. So in experiment 1 and 3, you can see now let's do this. Okay. As you go from experiment 1 to experiment 3, if you compare them both, A has increased by a factor of 4. You can now see that B has not increased, but look at the initial rate this time. It's gone from 2 to 8. That is also a factor of 4. So, therefore, the order of reaction with respect to A is first order, or 1, because the concentration of A has increased by the factor of 4, and therefore the initial rate has also increased by the factor of 4, so they're directly proportional. So we can actually write this as something called a rate expression. So I will be writing rate is equal to something called K. This is called the rate constant. We'll talk about that in later lessons. Equals, which is then multiplied by the concentration of A, square brackets means concentration. I'm going to put 1 for first order, times concentration of B, 1 for first order. And that would be our rate expression, our rate reaction, determined experimentally. Let's have a look at another example. So here we've got C plus D, let's say it reacts to form E. Okay, so experiment 1 and 2. Again, the first one, C, no increase in the concentration of C, but the concentration of D increases by a factor of 2. But look at the initial rate this time. There is no increase. So therefore, increasing the concentration of D does not increase initial rate. So, the order of reaction with respect to D is 0. No impact. Okay, let's have a look and compare experiment 1 to 3. Well, C this time has increased by a factor of 2, and D has not increased. And this time, the initial rate has actually increased by a factor of 4. So what's actually happened is, it's the increase in C has a change that is 2 squared on the initial rate. So because C is increased by a factor of 2, square of 2 is 4, so the initial rate increases by a factor of 4. This is called second order. So the order of reaction with respect to C is 2. Okay, let's write down the rate equation. So rate, as always, equals rate constant times the concentration of D, which is 0, times the concentration of C, which is 2. And actually, you would usually not include D in the rate equation as it has no impact. It's no impact. It's going to be constant. It doesn't matter. If I change the concentration of D up and down, it's not going to change the rate. So therefore, the rate equals K times the concentration of C squared. Okay, final example. There'll be some questions for you to answer in this one. Okay, we've got E reacting with F to form, let's say, G. So, this time, let's look at experiment 1 to 2. So we can see in experiment 1 to 2, there is no change in E. But in experiment F, the rate of reaction is halved. And if you look at the initial rate, the rate of reaction there is halved. So you're going to be asked now, which order of reaction is this with respect to F? Well, you should see that, well, if F divides by 2 and the initial rate also halves, the order of reaction with respect to F is 1. It's first order. It's exactly the same. If you're halving a concentration and the rate halves, it's exactly the same as if you double the concentration and the rate doubles. Let's look at the other reactant. Okay, so this time we're going to compare experiment 2 and 3. So, experiment 2, F, no change. But for the concentration of E, the concentration goes from 1 to 0.25. That is divided by 4. Well, let's look at what happens to the initial rate. The initial rate goes from 1 to 0.25. That is divided by 4. So, that means the order of reaction with respect to E is also 1. So if I was to write the rate equation, it would be rate equals K F1 and E1. And remember, we don't have to put these ones there if we don't need to. Okay, good.